Hi, I'm Sarvesh Deshmukh and I'm here to give a demo on the topic called object recognition in real time using Surf and OpenCV. And this is my course project at the University of Florida for the subject of pattern recognition EEL 6825 Spring 2017 batch. So let us start by introduction. So we are recognizing multiple objects in real time using OpenCV and Python. So basically, the task of identifying where the object in a video is one of the primary problems in the field of machine learning and as well as pattern recognition. So the importance of object recognition is evident from the fact that object recognition finds its application in a large number of areas, including security, sports, automated cars, and analysis. Moreover, it has become very important for computer vision systems to have object recognition capabilities in them. So, SURF is one such algorithm which is used to detect objects in real time, and it is very fast, so it is suitable for real time systems. Okay, so let me give you a demo of the project first, and then we'll go into more details about how this is done. Okay. Okay. So this is the first object which we will detect. So as you can see, the application has recognized this object. Basically what it does is it detects key points and then descriptors and then matches it with the training images. So one thing to notice here is surf is a scale invariant and also a rotation invariant. So even if I rotate this image, a system can still find this object. Now this is also a scale invariant. So if I zoom in or I zoom out, you will see the same corners detected and the same object getting detected. Moreover, if I flip it, you won't detect it because this image is not in my training database. Okay. One thing to notice here is as I go away from the screen, the object recognition capability decreases. See the object is not decreased beyond this distance. Okay. Now let us test it with the second object. So this is the object which we have used while giving the demo and presentations. Okay, so you can see the object is getting recognized. And third object, see, and moreover, surf is robust to noise. So even if I put my hand here, you'll still be able to detect this same notebook. Okay, rotate it. See, it is able to detect this too. Okay, so now let's go into detail. So, yeah, related work. See, the main concept on which this project works is we detect some key points and we calculate the descriptors for those key points, and then we match those descriptors with another image with which we have to match the query image. Okay. So the related work. So the first is Harris corner detector. This is most commonly used to detect corners, but this is not scale invariant, meaning that if you zoom in and zoom out, you may not see the same corners getting detected. Okay. Second is scale invariant feature transform, which is also called as shift. This algorithm is also used to detect objects, but the thing here is it does not use integral images to approximate Laplacian of Gaussian. So, and what the integral image is, I'll explain it in a later section. So, the Laplacian of Gaussian is approximated with difference of Gaussian in shift, and hence the speed is quite low of this algorithm, and hence it is not suitable for real-time application, and it is way slower than surf. So that's why we decided to go with surf algorithm to detect the objects in real time. Third is brute force matcher. The matcher comes into picture when we have already detected key points and computed its descriptors, and now we have to match descriptors from the query image and the training image. So the brute force matcher, what it does is it tries all possibilities and returns the best match. So as you can see, it is very intuitive that that this matcher is very slow for large data sets, and hence we have used flat based matcher, which is based on nearest neighbor matches, and I'll be explaining it in the later section. Okay, so now next, see, there are three stages for this application. Sorry, four stages. The first stage is detecting features, that is detecting key points. Second is obtain feature description vectors. Third is feature matching, where we match features from query image and training image. And fourth is feature matching combined with homography to find objects, in which we we find perspective transform, and then we detect the image, and then we draw a rectangle or any border around it. Okay, so next. So, oh sorry, let me zoom in. Okay, so this is the algorithm on which our application works. So first we initialize a surf algorithm, then we initialize the matcher object. For us this is flat based matcher, as I discussed earlier. Then we have a set of training images. For those images we detect the key points, and then we calculate those descriptors for those key points. Okay, next we initialize a video capture, and then we run it into while loop. Then we run a while loop, and then uh, whatever our video is capturing, we detect key points from it, and also we calculate the descriptors, and then we match this descriptor with the descriptors we have in our training images. So so, while we match those, we apply some distance ratio test for those matches. When our matches, when our matcher returns some matches, okay. So we apply the ratio test, and then if the ratio test is passed, that is based on some criteria which I'll explain later. So if that test is passed, then we say that the this match is good. Sorry, this match is best. Okay, and then when in the later stage, when a number of best matches is greater than some threshold. So for this example, we have set that threshold to 8. So if that number is greater than 8, we compute the homography and perspective transformation, and we draw the borders around our object, and then show it on the screen. So basically what we are doing here is we are calculating key points and descriptors for one image, and for another image we are calculating its key points and descriptors, and then we are matching it, and then our matcher returns some matches from it. We apply the ratio test to determine if this is the best match or not. Yes, so if this is the best match, we check how many matches it has written. So if that number is greater than 8, then we declare that the match is now found, sorry, the object is now found, and we draw border around it, and then we display it on the screen. Okay, okay, so the next slide is so step 1. So stage 1 was detecting features, right? Like for example, detecting key points. So in this we have used surf detector, which relies heavily on determinant of Hessian matrix, and also we looked at the demo that the surf is scale and rotation invariant, and we also explained the meaning of it. Also, one point to note here is in shift algorithm, the Laplacian of Gaussian is approximated with difference of Gaussian, but in surf, the the Laplacian of Gaussian is approximated with box filter, and we use the SURF uses integral image, which allows for the faster computation of the convolution box filters. Okay, so faster, why? Because when you use integral image, there are only constant time operations which we have to perform. There are only four addition subtraction operations which we'll explain. So, and also there are two versions of this SURF algorithm. One is upright version. Uh, that version we can use where we do not want uh, rotation invariance. For this project, we wanted rotation invariance, so we have used the normal version of SURF. Okay, sorry. So yeah, and the scale space is done by upscaling the size of the filter. So now if you see in SIFT algorithm, the the scale space analysis is done by progressively decreasing the size of an image. So here we are not decreasing the size of image, we are upscaling the image. Like we are applying the filters of progressively increasing size. Okay, so we are applying the masks of increasing size. So so here are some of the terms which I uh, discussed in the previous slide. The integral image. See, so this is the integral image. Okay. So the advantage of approximating Laplacian of Gaussian with box filter using integral images is it is easily calculated with the help of integral images, because you only have to do this computation. Now in integral image, to find the value of this point, let's say A. So to find a value of this point, you so the value of A equals to value of all the pixels above and to the left side of A. Okay, so this is the formula: D minus B minus C plus A. So this is, you can say this is a constant time application which helps in the low computational cost that this SURF algorithm gives us. Okay. So as we said, SURF uses box filters to approximate the Laplacian of Gaussian. So here you have an example of second order Gaussian partial derivatives in y direction and in xy direction, and you can see the approximation of the approximation of those Gaussian partial derivatives using the box filter. Okay, and this is a formula to calculate the value from integral image, as we said. Okay, yeah, and this is a Hessian matrix where L sub double x is the convolution of the Gaussian second order derivative with image in point x. So with the help of integral image, uh, we approximate the Laplacian of Gaussian with the help of integral image and box filters. Okay, next. Yeah. Now the scale space analysis. So as we discussed earlier, the analysis in SIFT was done using decreasing the size of image, that is downscaling the image. Whereas in SURF, what it does is it iteratively applies filters of increasing size. Okay. So like you can see the stage one, and then the next stage here. So 9 by 9 goes to 15 by 15, and then 21 by 21, like that. So we apply this increasing masks on the images. So basically we upscale the image for scale space analysis in SURF algorithm.